Episode 2: Operating the World, the code engines behind our computers. Computers rule our daily lives, but how do they actually run? In this episode, we peel back the screen to find the hidden engines, the operating systems and low-level code that quietly power everything from your laptop to your car. Imagine millions of lines of code humming in harmony, orchestrating modern life. It's a tale of unsung heroes, programs so foundational that we hardly notice them, yet so vital that without them, the digital world would crash to a halt. Segment 1: The Invisible Maestros, Introduction to Operating Systems. Every time you boot up your computer or tap your phone awake, an invisible conductor takes the stage. This conductor is the operating system, OS, a master program coordinating all other programs. In simple terms, an OS is to a computer what a brain is to a body, managing movements, memory, and communications. The first electronic computers had no operating systems at all. In the 1940s and early 50s, running a program meant manually flipping switches or feeding in stacks of punched cards to reconfigure the machine for each task. It was slow, cumbersome, and required a small army of technicians. Those rectangular punched cards, each storing maybe 80 characters of instructions, were once the primary medium for inputting programs. An engineer might carry boxes of cards, one box per program, to feed a mainframe computer. If one card had a typo or, heaven forbid, you dropped the deck, chaos ensued. These were the dark ages before operating systems, when computers obediently ran one program at a time and immediately halted, awaiting the next human command. The revolution came in the mid-1950s. As computers like the IBM 701 appeared in businesses, the need for automation grew. Enter the first rudimentary operating system, GMNAAIO, built in 1956 for the IBM 704. It could automatically load and run a new program as soon as the last one finished, rather than sitting idle. It was primitive, just a batch processing monitor. But it planted the seed. Through the 1960s, researchers, notably at MIT with projects like CTSS and Multics, imagined time-sharing, letting multiple users seemingly use the computer at once. The OS became a traffic cop, rapidly switching between tasks so that each user felt like they had the whole machine. This concept of time-sharing was revolutionary. A big IBM mainframe could serve dozens of people at teletypes simultaneously, and nobody realized the machine's attention was divided. By the late 60s and early 70s, operating systems had names that now loom legendary. Unix, for example, was born in 1969 out of the ashes of the overly ambitious Multics. Created by a handful of programmers at Bell Labs, Unix was elegant and small enough to run on early mini-computers, yet powerful in design. It introduced the idea of piping outputs to inputs, letting software tools be chained together like a factory line, a concept that lives on in today's Linux and Mac OS. Meanwhile, on the other side of the digital world, a young Bill Gates and Paul Allen wrote a very simple OS called Basic Interpreter for the Altair 8800 in 1975. And shortly after, Gates' Microsoft provided MS-DOS for IBM PCs in 1981. MS-DOS was a text-based, 16-bit operating system that fit in just 160 kilobytes of memory, minuscule by today's standards. Users interacted with it via a black screen and a blinking prompt, think C:, typing arcane commands to copy files or run programs. Segment 2: The PC Revolution and Open Source Empires. The 1980s brought an explosion. Computers left the glass-house data centers and landed on desks and in dens. Operating systems had to evolve to be friendlier, and so the graphical user interface, GUI, was born. Instead of cryptic text, users saw windows, icons, and buttons they could click. Apple's Macintosh, in 1984, famously introduced the masses to GUI-based OS with its cute trash can icon and menus, while Microsoft Windows, initially a mere add-on to DOS in 1985, gradually matured into the dominant OS by the 90s. PCs everywhere running, Windows 95, the startup sound chiming, the start button menu opening. The world had embraced an interface anyone could use, not just specialists. Behind that friendly GUI though, the same core duties applied. The OS managed files on disk, kept programs from stepping on each other in memory, and handled talking to printers and networks. It was the silent administrator making sure your click actually opened a program, and that two programs didn't grab the same resources and crash the machine. Meanwhile, an important movement was brewing quietly among programmers: the idea that operating systems, and software generally, could be open source, freely available for anyone to study, modify, and share. In 1991, a Finnish student named Linus Torvalds started a hobby project to create a free Unix-like kernel. He famously announced on a forum, "I'm doing a free operating system, just a hobby, won't be big and professional, like GNU." That hobby called Linux did indeed become big and professional. Over the ensuing decades, Linux, collaboratively developed by thousands around the globe, grew into a powerhouse. Today, Linux runs the majority of web servers, nearly all supercomputers, and every Android smartphone under the hood. Think about that. What began as one student's DIY project now powers billions of devices, an open source engine at the heart of modern computing. Open source operating systems proved something profound. When the source code is open for anyone to improve, you can marshal the wisdom of crowds. By 2017, 100% of the top 500 supercomputers in the world ran Linux because its reliability and flexibility were unmatched. The open source empire is real. Communities of developers building robust OSs like Linux and Android, itself a Linux-based OS by Google, that dominate markets. Even Microsoft, once the staunch defender of closed Windows, now incorporates Linux compatibility and open source components. The hobby OS that won't be big ended up everywhere, often invisible, but critical. Segment 3, Code in the Shadows, Firmware and Microcode. Not all operating code lives on hard drives and screens. Deep inside devices, there's code even closer to the metal, firmware and microcode that operate machinery directly. If the OS is the brain, firmware is like reflexes or the spinal cord, basic instructions that run hardware components. BIOS/UEFI, for instance, is firmware that kicks on when you power up your PC, initializing the hardware and then handing control to the OS. It's the code you see briefly as text on a black screen before Windows or Linux boots. Similarly, every modern car contains dozens of tiny computers, called ECUs, with firmware that control brakes, engine timing, airbags, and more. A modern car can have over 100 million lines of code spread across its systems, more code than a jetliner. How's that for surprising? In fact, top-end vehicles like the Ford F-150 truck run on 150 million plus lines of code and have around 150 microprocessors, coordinating everything from navigation to fuel injection. Without this embedded code, today's cars wouldn't run, literally. This invisible software monitors sensors and issues commands in real time, keeping you safely on the road. Even within CPUs themselves, there's microcode, low-level instructions that translate the complex instructions programmers write into the fundamental electronic signals that flip transistors. You could say there are operating systems within the silicon. These micro-instructions can sometimes be updated to fix hardware bugs, a mind-bending concept. You patch your processor with a firmware update so that the chip's own instruction set works around flaws. One dramatic example of firmware's importance came to light with the Pentium FDIV bug in 1994. Intel's flagship CPU had a tiny error in its division circuit, a hardware bug that could cause rare calculation mistakes. Intel addressed it partly by microcode updates to mitigate the issue until defective chips were replaced. And consider the aviation world. The software in a Boeing 787 Dreamliner or an Airbus A350 is staggeringly complex and must be bulletproof. In 2014, one estimate was that the Boeing 787 software exceeded 6 million lines of code, and that's just the avionics systems, not counting passenger entertainment. These aren't full operating systems like Windows, but rather specialized real-time operating systems, RTOS, and firmware that ensure every sensor reading and actuator command happens on time and in the right order. Segment 4. When operating code fails. Cautionary tales. With great code power comes great responsibility. A single flaw in the code engines running our world can spell disaster. One infamous incident was the Ariane 5 rocket explosion in 1996. The European Space Agency's shiny new rocket self-destructed 37 seconds after launch. The culprit? An uncaught software exception, essentially. A number, the rocket's horizontal velocity, got too big for the 16-bit register intended to store it, causing an overflow. The inertial guidance software had reused code from the older Ariane 4, not anticipating Ariane 5's higher speeds. This led to a cascade of failures, and the rocket veering off course, triggering self-destruction. The loss was over $370 million, making it one of the most expensive software bugs in history. It's a stark reminder that the low-level code controlling physical systems must be exhaustively tested. Nature's unforgiving when software directs tons of metal and fuel hurtling through the sky. Another sobering story. In 1990, AT&T's nationwide telephone network was knocked out for hours when a single line of buggy code in a routing switch caused a cascade of crashes across switching stations. 70 million phone calls didn't go through that day. Essentially, a subtle flaw in an if statement propagated, illustrating how even operating software for telephone exchanges, a kind of real-time OS for calls, needs near perfection. On a more positive note, good operating system design saved the day during Apollo 11's moon landing in 1969. As the lunar module descended, its onboard computer, the Apollo guidance computer running a primitive real-time OS, was overwhelmed with unnecessary radar data, triggering alarms 1202 and 1201, program alarms. Instead of crashing or rebooting, the software smartly shed low-priority tasks and focused on the critical ones, namely, landing the spacecraft safely. Margaret Hamilton and her team had designed the software with a feature akin to modern priority interrupt handling. Thanks to that foresight, even though the computer was briefly overloaded, it recovered gracefully in seconds and kept the lunar module on track for touchdown. Neil Armstrong and Buzz Aldrin touched down on the moon with only seconds of fuel to spare, all while the computer handled the strain elegantly. The term software engineering was actually popularized by this Apollo project, a recognition that coding these systems required the rigor of traditional engineering disciplines. Segment 5, the future. Operating the world quietly and everywhere. Today's world runs on an orchestra of operating systems big and small. Your smartphone contains not just one OS like Android or iOS, but also many firmwares. One for Bluetooth, one for Wi-Fi, one for the camera, etc. Cloud data centers where our websites and apps live rely on hypervisors and container OS layers, parceling hardware to virtual machines with incredible efficiency. We've arrived at an age where even light bulbs and toasters run micro OSs if they're smart IoT devices. This proliferation brings great convenience and new challenges. With code everywhere, the potential for bugs or cyber attacks rises. A chilling example, in 2016, the Mirai botnet hijacked thousands of security cameras and DVRs, each running a tiny Linux-based OS because they had default passwords. The botnet then launched a massive DDoS attack that briefly took down major websites across the globe. Suddenly, the importance of securing even the lowliest operating code became clear. Yet, the marvel outweighs the fear. We have cars with autopilot features that rely on real-time operating systems crunching sensor data from radar, cameras, and LiDAR to make split-second decisions. The code in a Tesla or other self-driving car is effectively an operating system for autonomous navigation, juggling vision processing, path planning, motor control, and more, all with life or death consequences for mistakes. In hospitals, advanced infusion pumps and pacemakers have embedded OS code to ensure dosages and heartbeats are regulated precisely. Even in entertainment, your gaming console or smart TV runs an OS that seamlessly streams content or renders 3D graphics on command. Operating systems truly operate the world. They're the unsung code that changed everything, by making complex technology usable, reliable, and scalable. Next time your computer boots in seconds, remember when it used to take minutes? Or your car smoothly navigates rush hour traffic? Or you ask a voice assistant a question and get an instant answer? Thank the invisible software orchestrators. They evolved from those humble, clunky beginnings of the 1950s into the sophisticated, robust systems now ingrained in every aspect of modern life. They keep planes in the sky, money flowing through banks, power grids balanced, and communications instantaneous. In the grand symphony of the code that changed the world, operating systems play the fundamental rhythms, steady and often unheard, but critical for everything to stay in tune. In the next episode, we'll connect the dots of communication. From the telegraph to the internet, discover how code has wired the world and shrunk the globe. Stay with us as our journey continues.